Without any further ado, so let's start today's tutorial. So I would say it's more like a experience sharing working with the large language models. And in particular, we want to highlight the relationship between the large language model to the AI load and also the constraints as well as the challenge to the power grids. Right. So here is just a very brief introduction about where do we come from. So we are coming from the ECE department of the University of Alberta. U of A is a top engineering schools. We have one of the largest engineering departments in Canada, and we are located in Edmonton, which is also the capital city for the Alberta province. We start from the background, and we will try to analyze and also give a high-level overview of the characteristic of AI loads. And then we will talk about how do we model or make it more clearly to characterize the dynamic behavior, especially the transient behavior about the AI loads. And we will also try to figure out several possible research directions. And we all feel that the large language model not only gave us a lot of opportunities, but also essentially there are still many unexplored and also many challenges left for our power engineers to contribute and make sure the large language model is kind of accessible, easily accessible, and also generalizable to all the tasks. Okay, so I think everyone in this meeting room will definitely recognize, right? So the AI is kind of booming again. So it's actually the largest wave so far, compared to the NFTs or metaverse, which has been also very hot topics in the last 3 to 5 years. The AI boom is definitely transforming our life a lot. Right. So compared to the previous, say, first to the third, we will call this a wave of AI. So the fourth time wave of AI is more comprehensive, including more industry and giving more transformation to our society. And is indeed coming very fast, right? So starting from around year 2020, when the OpenAI published the GPT-2 model, all the researchers still thought, okay, so AI may come in such a large angular way, but we may still invest on more smaller models or some other branches of AI. Well, over the past 4 years, right? So starting from the GPT-2, the model parameters are becoming much larger and larger, while the model performance is also becoming much higher. And this is a so-called scaling law. Basically, the performance of the large language model is scaled linearly or even exponentially with respect to the model parameters. And in observation of such evolving fast open AI model, right? So it's still giving a lot of newer and also more and more amazing capabilities. For instance, like the OpenAI O1, which was published 2 weeks ago. Right? So in this O1 model, essentially we are highlighting OpenAI will highlighting the capability of chain of thoughts. And through the reinforcement learning, the O1 model can improve a lot over the original GPT-4 model or ChatGPT model over the abilities of reasoning, refining strategies, and learning from the mistakes. And essentially, such capabilities coming from the breaking down of some complex tasks. And in their benchmark, they already show such LLM model combined with this chain of thought capabilities can achieve even superior performance in mathematics, some language understanding, and also conversation. Right? So these are really amazing rules. And they just made a joke, right? So for the large language model with OpenAI O1, it can hold several PhD degrees together in mathematics, engineering, philosophy, and also laws. Right. If I give it a really quick try, right? So here was also the result I showed. I tried last week, right? So if I try to instruct the O1 model, the OpenAI O1 model with an optimal power flow example, say we have 3 buses, which is shown on the left-hand side. And we try to solve this optimal power flow problem directly using OpenAI. And after 80 seconds of thoughts, the O1 model will try firstly, right, to try to reiterate, right? So what do I mean by my natural language, right? So what is the cost for each bus, for each generator, and what are the variables, and what are the constraints? And by firstly formulating the problem, the OpenAI O1 model can also solve it step by step. And the results are quite accurate. And in other work, so which is kind of independent to this work, we also show the large language model can indeed help the power system to achieve certain tasks. For example, like the power system operations, such as solving optimal power flow, economic dispatch, or even unit commitment, and also achieving some multi-model capability. For instance, trying to directly use the images to do the state estimation or do situation awareness. If the audience are interested, we will also advertise this work on the bottom of this slide. So feel free to check the our overview of the capabilities of large language model in power systems. Well, today's talk is not only related to the fast deployment of the amazing capabilities of the AI provided to the power system. It's more on the reverse side, right? So if we are using this kind of larger model, what will be the effect to the power grids? So that is very important because essentially the Gen AI, the large language model, some diffusion models can be really huge energy hogs. So here I just show a screenshot from a Reddit conversation. So essentially they actually do this kind of pair-to-pair or apple-to-apple comparison. So using a Google search query, you are only use a very small fraction of electricity, so only 1.0 kg. Well, if I'm using a ChatGPT query, right, so the energy you use is even 10 times or even 100 times larger, right? So this is essentially, right, so if you're say all doing the search task, well, Google can give you a set of results, although the result may not be the ideal, based on some research, right, so compared to ChatGPT, well, the energy consumption essentially is much smaller. Well, at the same time, due to the fast development of AI, we already saw the greenhouse gas emission cut nearly 50% based on Google's report. And globally, right, so we are seeing the AI-related data center and AI power is also growing at a very fast pace. Well, this is more like from the overall picture, right? So we need more and more electricity, we need more and more energy to power our AI developments. Well, on a more specific level, right? So previously we saw the fast development of NVIDIA GPUs, and the large language model inference and training is highly constrained by the resources. For example, like the GPU capabilities or the size of your GPUs or your different devices. Well, in the long run, we will envision the reliable operations and reliable services of large language model is highly dependent on the power and energy infrastructure. And for instance, this is news is actually coming from last week. The Microsoft actually reached a deal with the Pennsylvania government to reopen the 3 Mile Island nuclear plant. And right, so this one was once termed as one of the worst nuclear reactor accident in the history of America. But now they try to reopen this nuclear reactor to make sure they have enough electric supply in a reliable form for their AI platforms. Okay, so this motivates us to do more research on this field, essentially to say, okay, by using more AI, right, so what will be the constraint to our power grids? Well, on the reverse side, is our current power system infrastructure will be reliable enough to support all the AI explosions. And if we are talking about the overall picture of the micro power consumption, right? So we can see the AI load or the AI electricity consumption is actually the largest contributing role of the overall power systems. And not only this is coming from different large companies, but for different models, right? So for example, in Google Cloud, they already have a very good benchmark to denote for each large language model, what will be the training time, what will be the training power consumption, and what will be the total carbon emissions. And what we found here is actually, it's also kind of like following the scaling law. So starting from, say, a relatively small number of parameters, like the GPT-2 or the BERT model, which was 5 years ago, right? So we only had within 15 megawatts hour of power energy consumption. Well, for current modern AI, like the Llama 3 or the GPT-4 model, right? So the number of parameters increase exponentially, while the energy consumption is also increasing exponentially. And indeed, right, so if we start from the say around 1998, was the last wave of AI is booming, right? So the model parameter is relatively small. We don't have around 6,000 parameters. And using single GPU, we train the model within say several watts of powers or several hundred watts of powers. Well, if we move forward to AlexNet, it's already becoming larger by using GPUs. And now GPT-3, they use over 10 to the 5 GPUs. Well, for the GPT MOE, which is short for the mix of experts, we use over the 13 terabytes of tokens, meaning over 13 terabytes of, you can treat it as a training samples or training segments. Well, due to the existence of training 1.8 terabytes parameters, we use over 10 to the 5 number of GPUs. And so essentially, the more GPUs, each GPU is already, say, around 1 kilowatts of power consumption, then the total power consumption will be huge. And it's already estimated, right? So the AI will be the largest single contributor of electricity demand increase in the North America in the next, say, 20 to 30 years. So essentially what we saw from the demand side is that for the past 20 years, the load was increasing at a very steady and very small pace. Well, for the next 30 years, the load increase will be largely coming from the AI and data centers. And so nowadays, right, so our data center design already tried to scale up to over gigawatts hour. Well, the challenge is not only about the scale. And in this talk, we are looking into a more hidden challenge, right? So first one, like we mentioned, is about the scale of the total energy or total power we need to supply our AI infrastructure. Well, at the same time, we need to talk about the speed, right? Essentially, right now, if we are using the ChatGPT or using some other chatbot or generative AI applications, we really want to have the answer instantly. So within 3 or 5 seconds wait, we want to get the answer, right? But from the GPU side or from the infrastructure side, right? So that means we need to ramp up for this kind of AI load in relatively instant time, right? So for instance, we want to get the GPU calculation done, right? So we need to ramp up to start the inference procedure instantly. So this means we need to have both a high bandwidth for the data transfer and also to have a low latency between the user's prompts to the final answer and inferences. Well, at the same time, right, so we observe actually in our simulation, there are a lot of chaos. And we term it as chaos because there are many unexpected or unknown behaviors that is coming to the AI load. For instance, there will be a lot of unplanned stop. Say, for instance, the GPU clusters will suddenly stop working, which we will give some examples in the later part of this lecture, sorry, in this talk. And so this kind of stop will be unpredictable. And also the AI load will be highly sensitive to the algorithm design. So for instance, if we start the different procedure of the large language model, say doing inference or doing some fine tuning or doing some retrieval augmented generation, essentially the AI load will behave in very different ways. And this can be also very related to the customer or the user behavior, which causes a lot of stochasticity. And in the latter part of the talk, we will also try to highlight, right? So due to this kind of stochasticity, we actually bring a lot of transient behaviors and bring a lot of unexpected storm to our power grid operations. So the general lesson or the key message we want to deliver from this seminar is that our traditional designs and operational power grid may not be well fitted for the AI applications. Well, although right now, right, so most of the power analysis or the electricity analysis is based on the chip level, say maybe more related to the power electronics or the chip design. So we want to have a higher power density, better voltage regulators, and also good power supply units. Well, at the same time, it's more moving further and further to the data center level as well as the grid level, right? So for instance, from the data center level, we want to have the good contract between the utility companies to the data center operator to make sure we have the uninterruptible power supplies. Well, from the AI computing side, people are also quite interested in the sustainability of data center. So how can we sustain the clean energy or the 24/7 clean power and carbon-free power to the data centers? Well, from the grid level, the constraints are coming from several perspectives. So one is based on the current grid model or based on the current grid connections, can we sustain the ever-increasing load from the AI side? Well, from the other side, so suppose there will behavior coming from a bunch of cluster of data centers, which can serve millions of customers. Well, all the customers will give certain prompts at certain time. So there will be spikes and also big stochasticity in the AI load, right? So is our current design can make sure the data center and the grid operation reliable? Right? So that's the question we want to question and also answer in this talk. And one thing to notice here is so far, based on our observations and investigations, the majority of the computing companies like Microsoft, Google, or Meta, they are not willing to disclose such data on the data center design or the interaction with the power system. And so this means although they can exploit or just make sure, right? So the model parameters is kind of known. I'll say the total energy consumption is revealed to the public, while for the transient behavior or the AI center dynamics is kind of unknown. And such kind of unknown information actually bring additional challenge for accommodating and designing more AI-oriented power infrastructures. So next, I will go into the characteristic of some AI loads, right? So if you are talking about the current general AI, it's actually still a machine learning model, right? So it still follows the general line, starting from simpler model to more advanced, bigger model, right? So starting from the statistics model, we may have linear or nonlinear functions, while deep neural network just to scale up the model with more layers and more nonlinear relatives between the layer. And by using the stochastic gradient descent, we can train the deep neural network well these days. And for the large language model, so we can still treat it as a neural network, but essentially we have more data and more neurons. And so that means we need more compute and more power to train the models. And there will be several tiers of data centers. And today we are more in the tier 3 and tier 4. So we wanted it to be fault tolerant, and also the data center need to work more reliably by using the electricity powers. And for designing the data center, it's not only about the GPU or the CPU, it's more like a whole system with the error handling units, some chiller, some UPS, which is for the uninterruptible power sources, and also integration from the renewable or other grid generations. Well, for current more advanced GPU, for instance, like this H100, which was integrated into the NVIDIA DGX system. So for this one set of DGX system, where their max claimed power consumption is 10 to the 2 kilowatts, which was including 8 H100 GPUs. And most of the time, if you are training the AI load based on the news and those observations, they often reach the 9 to 10 kilowatts under the full load. And for model training, if you are talking about the large language model, essentially we are not just using one single H100 GPU or one single DGX as a computing power. For instance, like the Llama 3 model, for the 70 billion model, it took around 7 million H100 hours. And if we are targeted at 1 month training time, so the single training task power, we are talking about the peak power is around 1 megawatts. Well, for the model inference, it's another picture, right? So for instance, right now, based on the Llama 3 report, only 10% of GPU are served for training tasks. Well, the other GPUs are essentially used for the inference tasks because more and more users are using the large models. And for serving one request, right? So for instance, if I just send a prompt to Meta's Llama model, that will use around 10 A100 GPU at this moment. So this means for serving one customer, right? So you are using around the peak power rate is around 12 kilowatts, right? Not a small number. Especially we are considering millions of customers may use the same model at the same time simultaneously. That will definitely incur unseen this kind of power interruptions to the current power loads. Okay. And if we talk about the inside of the GPU, right? So essentially there are different ways to parallelize the computation by the pipeline tensor of data. Well, all this parallelization will, as a one side, to accelerate the computation, well, as the other side, will just to make sure the power instance will becoming much larger and also becoming much more instantly. Okay. So here is a design from the Schneider about the AI data center. So right now we are moving more and more retrofitting for the traditional data center to the AI data centers. And to accommodate the AI load, some design principles are like this. Right? So one is for AI specific load can be really large. So we want to serve it more reliable with power supply. Well, we are moving towards the gigawatt data centers and needs to be higher reliable against service interruptions. Meaning if we have several loads coming simultaneously, we want to serve them all well with very low latency. And at the same time, we want to make sure the GPU are working at a certain temperature and within certain load. And for the generative AI pipeline, right? So we can, we're talking about the power load. We are not only talking about certain stage, say training the model or inference model. Essentially, the generative AI has a very dedicated and also multi-stage pipeline, starting from the pre-training, where a lot of data need to be prepared. We need to co-start the GPU. And after the training, we have a lot of procedures. Right now, we have something called the chain of thought, like the O1 model, or using the RLHF. And for fine tuning, we have the models of some external data. And for the inferences, yeah, it will be more interaction with the users and a lot of cold start and also sharp end for each sessions. And for transformers, right, essentially, this is a working house for any large language model. So it's a sequential, we can treat it as a combination of both sequential model and also very dense and also very complicated connections between layer by layer, where we use a K, Q, and V for K query and the value to calculate the final values. And we can also use a lot of documents to feed into the model to get a better answer. And so far, right, so for instance, like the training procedure, yeah, it's also can encounter some issue. So for instance, like when I'm training the Llama 3, the report set, there will be around 54-day period of Llama 3 pre-training. And there are over 200 or 300 instances which are interrupted, right? And for all these interrupted tasks or interrupted jobs, 78% of them are due to the hardware issue. So meaning that nowadays, if I'm serving a cluster of GPUs in parallel, there will be a lot of interruptions. And for once the interruption happens, it will incur another very sharp power chain due to the each GPU can consume a lot of power. So the sum of the GPU is definitely giving a lot of interruption to the power grid. And essentially, right, so for the future, even larger scale implementation, we need to consider this kind of transient behavior and transient care caused by these kind of interruptions. Right. And so here we just give a quick table for the different stage for the RM training and also model serving. Yeah, essentially, yeah, each stage have distinct characteristics. And so far as we know, from both the power utility or power industry and also from the data center or the AI side, we don't have such a good characterization of each stage power consumption characteristics versus the power system operation skill. In particular, in the distribution level, if I'm talking about the current infrastructures, can we actually sustain with the current infrastructures and the power supply solely coming from the energy storage or solely coming from the renewables. So yeah, so this will be my part for giving an overall analysis or overall picture about the power system and the AI load. I will refer the remaining time to my colleagues, Yuzhou, who will giving more detailed analysis on our simulation result and case studies for the AI power load.
Thank you. Thank Dr. Chen for the very comprehensive overview and everything. So I will share my screen here and continue our talk about this interesting topic. So give me a second to share. So I will just present. Is this good?
Yes.
Okay. So we're going to talk about the power consumption modeling of AI workloads and following some case studies and other future directions. So firstly, I really want to highlight this problem, like how the LLM trained. Like the model side is more related to the computer science community, but in this particular topic, we actually do care about how the model trained. So in current state, the model normally deal with the big data set from gigabyte to terabyte. And we also dealing with millions or even trillions, billions, trillions parameters. The model is pretty large. And also we have a limited GPU count. This is the time like people want to develop some efficient method to enable the training. So for the data side, we can break down the data into several pieces. And for the model side, we can just load into the GPU, and each GPU will dealing with a slice of the data. Once it's loaded, we can initialize the parameter. And I forgot to mention, like this demo is just a very simple case based on Microsoft methods called DeepSpeed. This is a training framework to speed up and make the training very efficient on the limited quantity of GPU. Very typical, very classical method. So at the beginning stage of this training cycle, each GPU will only hold like a quarter of parameters. This makes sure the GPU can just contain like only the necessary memory and the parameter inside the memory. So at the beginning of the training cycle, the algorithm just need to broadcast the model parameter like from the first GPU to other GPU, sharing all the parameter with each other. So this actually introduced the data transfer power. After the broadcast end, then each GPU will have the parameter of the model. Then we can start this forward calculation. So we will see like in each GPU, the calculation happen. This means the calculation cost will introduce the power, like a power surge. So this will keep going like from second GPU broadcast the parameter to others, and we do this forward calculation. And then the third GPU share the parameters, and then the fourth GPU share the parameters. So at the end, then we can calculate the loss. Please notice like this loss is actually related to data slice. It's not complete. So what we're gonna do, we're gonna just do this back propagation process to just calculate the gradients of the whole model. So the parameter in the fourth GPU, we start this from the end now. So the parameters in the first GPU will start to broadcast to other GPUs. So this causes like a data transfer for sure. And then the parameter gradients will be calculated in each GPUs. And this causes like a calculation power surge. And this continue, the whole procedure will just like the reverse process of the forward path. Then it will just continue until the end. So at the end, all the GPU has this their calculated gradients, right? So what we do is to enable this optimizer to just calculate the revised parameter or the like a more accurate parameter to update the model, right? So this involves intense calculation until the end. For example, in this particular case, optimizer will give the flow point 32 revised parameter for each GPU. This is a very intense calculation. And then it can convert to flow point 16. So this is a data type conversion. And then the model will have this revised or updated parameter. This ends the training cycle. We from this simple case, we see the LLM model. Actually, the whole training involves a lot of different stages, very complicated procedure of data transfer and the training calculation. They involve different kind of like a power level. In a general bigger picture, we see like in the data center, AI-centric data center, this layered power consumption model. So in the total, we see the data center consume the power either from utility or external power source, like the renewable generation, natural gas, even nuclear power or fuel oils. And in power supply side, if we focus on the utility side, then we can just separate the power consumption into like a supporting infrastructure and also the IT power like IT power consumption. And inside the IT power consumption, we had the servers. And also inside the server, we had the AI compute involved power consumption and other computation power consumption. If we really dig deep, we will notice like the AI computation actually introduced the major power consumption in the AI-centric data center. So here we start from the outer layer. So if we look at the data center example shown here, we can just give this general equation. The P total equal to the P AC bus plus the P external. Then we can just, if we like ignore the external power source, then if we focus on the AI bus, I mean the AC bus, then we can just decompose into supporting infrastructure and IT power consumption. And if we just decompose into more detail, like finer detail, then we can just notice like the supporting infrastructure consists a lot of like auxiliary components. And also for the IT power consumption, we can just decompose into the server, the network, the storage, and all the others. Well, for sure, we particular focus is on the IT power consumption. So here, like the server actually deal with the major computation jobs, and we just really focusing or really feel like interest on the AI side. So the AI side in a steady state, we can just use this like a rough equation to describe. We can just use the N as the number of the AI accelerators, normally it's GPU, and the peak power, like normally defined or very close to the TDP, and also the phases means like we can just separate the phase as a factor, like separate based on the pre-training, post-training, fine-tune, or inferences. So this gives us the steady state, but this is clearly not enough, right? So we more like based on Dr. Chen's introduction, like we know the AI training and running actually very dynamic. It involves a lot of like a complicated process inside. So if we look at this in a dynamic state, in a dynamic way, then the power consumed by the AI computation roughly equal to the AI accelerators. And this can be further decomposed into the compute module and the memory, the cooling, and the auxiliaries. Then the training side, actually, we can just use this roughly approximate based on the base power consumption and also the each node, like each individual calculating components. The fine tune is a little bit slightly different, but very close to the training consumption. We can just describe this as a base load plus the node, like the computation node, and multiply by this factor. This is time changing factor, like really depends on the algorithm side. The inference is more like related to the user behavior. So we can just basically use this kind of statistical description for that. And if we combine all these three stage or all the dynamics together, we can have this power consumption of AI equal to power of training, power of fine tuning, and power of inference. And they will multiply by a time varying factor, like based on the ratio or based on the load condition. This basically gave this very rough, like a high level mathematical description of this power consumption. And we know like this, there's much more need to do. Starting from here, we can just really dig into the training stage and the fine-tuning stage, inference stage. We can just look into like what's going on inside the algorithm, what's going on with the user behavior and more. We just we treat this like a starting point. So following that, we want to show some case studies about the power consumption and with some analysis. What we're looking at, we actually want to looking at how AI run in a data center, like the power consumption from data center side, and also like how the AI run in local settings, like the workstation. For the data center, luckily we found a data set from MIT SuperCloud. There's like hundreds of GPUs inside, and also like a 7 months plus data recording. So there's a lot of information there. For the local workstation, we set up our own like hardware, like based on NVIDIA GPUs and also AMD GPUs, and also like mainly dealing with like a different AI computation stage for small language models. So here is the data center behavior. We just summarize in this figure. As we can see, like the 7 months GPU consumption is very dynamic. Somehow, like even hardly to conclude any pattern, like the periodical patterns inside. And we can notice like the dynamic range can start from 0 to above 50 kilowatt. And also like there's a lot power spikes inside. And also once the GPU or the cluster got activated, the power consumption normally be above 10 kilowatts. And there's more like statistical insights. Like for example, the median power is around like a 30 kilowatt. This indicates the typical operation use about 50 or 60 GPUs. And also it has a very wide distribution. And also like somehow the curve is considerably smooth. And this means like the job is quite diverse. The jobs are very diverse. And also like for the distribution, the probabilistic density function, we can say a bi-model distribution somehow exists. And also in the low power mode, the peak is around like 5 kilowatt. For the high power mode, the peak is around 30 kilowatt. And there's a long upper tail extend to like extremely high, but it's rarely happen during this data center data record. There's several noticeable moments, actually very interesting. I actually plot like more than 600 events, but 3 of them is a particular interesting to me. Like the first one, let me try to use my mouse here, like if anyone can see. Oh no, not I know. Okay, so let me just using my mouse to describe. So we can see a dynamic, like a sharp power swing, like from 70 kilowatt to 0. This is a very, very sharp and very quick dynamic change. This probably means like the model like running in a peak power level and then suddenly stop. And there's another example like showing like the sharp spikes following by quick returns to the baseline. Is the bottom right side. Like we see this continuously happen. Somehow like the model or the GPU just reached to a really high power consumption level and then drop back and then going to peak again and then drop back. And then we also observe some regular cycles, like those cycles between 20 kilowatts to 24 kilowatts. So if we dig deeper about this data center behavior, based on the MIT SuperCloud, the paper, this describe the jobs actually very diverse as we observe based on the statistical figures. Actually, it involves a lot of different AI algorithms, but this is not all of the computation. Well, for particular interest, we do notice we do want to highlight the BERT inside this data set. The BERT actually is a quite famous, very typical classical large language model. And this figure shows like the power consumption of the BERT. Actually, it can reach really high about this power consumption. The peak power consumption is around 50 kilowatts, and with average is around like 17 or 18 kilowatts. And this drop runs like roughly around 4 days. We can imagine like some research group must work on this data center and just for 4 days. So in detail, we can observe some interesting dynamic behavior inside. For example, like the power ramping can just happen at the beginning stage of the training, and the figure like upper right-hand side shows like the 20 kilowatt browserly 20 kilowatt power ramping happen really quick. Oh, that's fine. Like somebody just jumping, like getting too excited. Okay, so the left bottom side, we also can observe some power decline happen, like a 26 kilowatt. And also we can observe like the power oscillation happen during certain time ranges. So let's move on to like the local running LLMs based on our hardware setting. So here we want to really look into the different like the training, fine tuning, and the inference stage, the power consumption of different models, different settings. The models we talk about here like cover a lot of different ones from GPT-2, like the classical one, the Nano GPT, until the new more like advanced one like Mamba, and even the latest the Llama 3.2 is just released I think 2 days ago. We finally just somehow managed to test it as well here. So the first case here showing here is about the LLM training on the NVIDIA GPU. We can just observe like a really steady peak power consumption until the end of the training cycle, and there's some spikes like the sharp power drop during the checkpoint. This is very interesting and unique. If we just zoom in, we can observe like just as the BERT, but in a very like a smaller scale, like the power decline happen like within 2 seconds, and also the power ramping happen like in a similar time scale. Another testing we do is do the Nano GPT training on the AMD GPU. Just roughly by observation, we can already see this one, the training power consumption is not so steady, is not so stable somehow. This is related to how optimized the algorithm be prepared. So we do observe some like the high harmonics in the power consumption curve. And also if we look inside look more detail about the power consumption, we also can observe the power decline happen and the power ramping also happen. So next, we also do this fine-tuning test for the LLM. It shows really interesting like different stages, even within this fine-tuning process. We can just basically decompose this process. Well, it is. I should highlight this. This is very algorithm determined behavior. So if you try different algorithm for fine tuning or even for the training, you will have a completely different power consumption somehow. Well, let's go back to this case. So for this fine tuning case, we decompose into 4 stages. The first stage is from 0 to 350 seconds. This is like the warm up of this whole fine-tuning process. It involves like an initialization of the algorithm, the data load in, and also like the parameter initialization. This involves very little power consumption, as we can observe. And moving on to like a second stage, we can observe like the rapid change power consumption, like the peak, the surge and the dip about the power. This actually introduced by the evaluation intervals. This is the algorithm evaluate the performance of this model based on the fine-tuning dataset. And if we moving a little bit like longer in the later half of this stage, we see like more like a steady behavior of the power consumption. So after this stage, the third stage, we reach to this very steady phase. In this phase, like the power consumption is really similar to the training stage, and the learning rate will enter this so-called decay phase. And we can observe like even in this fine-tuning stage, the second stage and the second phase and the third phase really exhibit totally different power behavior somehow. At the end, it's just a checkpoint and just shut down all the algorithms. So the power consumption go to 0 somehow. Not 0, like near 0, the idle power consumption. So here's another big set of the case studies we want to focus on. It's about the model inference. Like this one, we do test about the Llama 3.2, 1 billion, 3 billion model with like 2 different query. From this diagram, we can see something very interesting. Each query like somehow introduce different power consumption, and the power consumption and even the energy consumption are totally different. Clearly, by reading the query, you can see the query 1 is simpler than query 2. And also, like if we think about the model size, clearly large model consume more power. Yeah. And then we also did this chain of thought case study. It's based on the Llama 3.1 8 billion model. And this is based on the open source project and try to mimic the OpenAI newly released model O1 behavior. So here's we try several different prompts and let the model run with chain of thought process to give us a better answer. So we want to highlight like several here, like for example, the prompt 1. So remember, we also like run this in the Llama 3.2 case. Here, with the chain of thought, we can observe several peak power consumption exist. This corresponds to the chain of thought steps. If we look at the step 1, 2, 3, 4, and until the final, this exactly can reflect in its power consumption curve. If we go to the prompt 6, this one clearly looks more complicated to the model. So based on the chain of thought process, this model take 8 steps and give the final answer. So we can observe the 8 peaks, 9 peaks actually during this power consumption in the power consumption curve. This gave us a hint that even though the OpenAI new model gave a better reasoning performance somehow, it indeed introduced a lot more energy and power consumption. It introduced more power transients during the generation of the final results. And also very interesting is that the chain of thought, they mainly do not control how many steps the model want to go. But actually, you can have you can have a very hard limit on the number of steps the model can go. But to get the better answer, you let the model go with the model like the behavior. I mean, this number of steps is not so deterministic. It's more like a statical, like a thing. And also we want to we already done some other inference tests based on different batch sizes. These tests show 2 models running with different batch sizes. First is Mamba and another is Transformer, very typical one. And with the increase of the batch size, the power consumption of Mamba actually, this is highlighted by the gray area. So the Mamba actually do not fluctuate or change too much. But for the Transformer side, like with the higher batch size, it just gradually increase the power consumption. And also one particularly interesting thing is like with a higher batch size, the Transformer require more memory, and our hardware just reached to the maximum available memory, so the model stopped working. And on the other side, the Mamba actually have a really better utilization of the hardware, and it can go to really high, like a really huge batch size. Consider our limited hardware capability. So here's more detail in the large language model inference. If we decompose the inference stage, we can just have these 2 different phases. One is called prompt phase, and the other is token generate phase. If we just put this really simple, we can imagine the model actually take this prompt phase as a process of what do you mean by your question, and somehow try to understand your question. And then the token generate phase is like to, based on his understanding or its understanding, it generates your answer. These 2 phases actually have different power consumption model. Well, this work is based on like Microsoft really interesting work published in 2024. So here's conclude all the insights based on all the case studies we have been done. So we do see a lot of dynamics in the model training, fine-tuning, and inference. They introduce significant power fluctuations, and also like the rapid power fluctuation, it's like happen everywhere. And the power surge almost like reach to peaks of the hardware. And for inference, for fine-tuning, for the training, they can all reach to the peak power consumption. But they somehow demonstrate a totally different like a spectrum features. In the more detailed way, like software side, the model architecture and the size will significantly impact the power consumption. We see this based on our case study. And also we notice like a smaller or efficient focus model, they can show some more variable power consumption. We're not saying like this model like it's not good or bad, but they show some more variable power consumption with frequent fluctuations. Really interesting behavior. And as I mentioned, like distinct training phases, they also introduced some unique power consumption patterns. The phases like the learning rate, like the warm up, really introduce some high like fluctuating power consumptions. This can be seen in fine tuning stage. From the hardware side, what we can observe is like each GPU can experience like the power swing from the peak to the idle, like within a second or even like a sub-second during the training stage, and during the fine-tuning and the inference stage as well. And also like different GPU manufacturers actually will lead to somehow like a varied power consumption. And also like a different GPU architecture and power management will affect the power consumption as well. Like this gave us the hint to think about how we can deal with those rapid power fluctuations. Next, we can just talk about like based on what we observed and what we studied, the future research direction. Here is the big background. Like when we talk about AI or large language model, people will argue this is just the fourth wave of AI hype, and this is a big bubble, and eventually this bubble will just vanish. But here is the statistical, like the survey shows a bit different from the previous three AI revolution. So this time, talk about the scale, the anticipation, and also the economy level. Everything is bigger. The AI market is expected to reach like 400 billion by 2027. And in the United States, people just estimate AI will just have an estimate 21% net increase on the United States GPU by 2030. And it's very interesting to see like a survey shows half of the US mobile user use voice search every day. And also like more data shows like the users, the manufacturers, the whole society just seems majorly opposite about the AI development. So to answer this, like, do we need more AI? I think the answer is yes. And consider the hype cycle of AI, we reach to the peak for sure, but also consider the longer term. This is only the beginning stage. Yeah, this means in the future AI will increase probably dramatically and in a larger scale. That also mentioned in the first half of the presentation. We will see more AI data center, more power consumption, and more transients to the grid. So what that mean? That means like we should focus in not only from not only on the AI for the grid. You know, like there's a lot of research talk about how AI algorithm can help grid research or grid industry. But also we need to focus on the grid for AI. It means like the grid side, we need to be prepared for AI. So here we decompose like into three main sectors, like talk about the challenge and opportunities. Like the first is the user side, the second is the data center side, and also the grid side. From the AI user side, we probably want to focusing on the power, the so-called power-aware AI training, fine-tuning, and inference. This means like when you design or do this training, fine-tuning, and inference, you probably want to care about how your algorithm, how the power consumption of your algorithm. So like a special design, like control the ramping rate of the power, control the timing of the checkpoint, so that you can avoid the large transients you introduce to the grid, to the local distribution system. And also like transparent and explainable AI is also very important, because to the outsiders, like the grid operator or the data center operator, they want to know like what's going on with the data center. The AI load, even though they designed by the algorithm, but also you can consider this as the power load, obviously, right? So you want to know really what's inside the AI load, and in each different stage, what calculation number of each steps, what this calculation convey to power consumption in each step. And also like we can look at the green AI algorithms, so means that we can develop or use efficient AI algorithm for for our smart grid or power system. Well, here shows a very recent research from our group study like two very special algorithm. One is called like a KAN. This is quite famous recent month, and another called liquid neural network. They are very small but very powerful, and consume considerably less power, and it can use for as an efficient AI for the smart grid. And also like moving to the data center perspective, we know we already know like a AI highly chances it will introduce some more dynamics to the system, even in the data center, right? So the power pattern model is very critical here. So we want to know how the AI really works. We try to describe by the mathematical, but we know like it's just a very general term. We need to do more on that. We need to have the accurate model as accurate as possible. And also like consider different time scale of AI behavior. We probably want to do this like hierarchical operation management. We also like want to focusing on like advanced power supply and the cooling to give a really good support for the AI load. And also a very unique thing is about how to compensate the power ramping and decline. Here is an example like showing if we integrate energy storage with the UPS, like the hybrid energy storage with UPS, then probably we can use the UPS to absorb this dynamic transients, and then the AI workload power transient probably will be compensated, and for the utility, the data center in general, the data center will be very constant. And also like if we consider a microgrid system, right? So inside the microgrid system, actually, if we consider data center somehow as a very independent system, this is happening actually, I forgot to mention. So people talk about a really large scale, gigawatt scale data center, right? They are trying to departure from a utility, and they want to include like a nuclear power, and then they want to form a very large scale microgrid running everything inside. So they can just speed up everything, get rid of the utility approval and everything. So here's the chance like the microgrid can really just be a really central concept in the data center power system. So a microgrid typically have a different functions span over like from milliseconds to days, even months. So from primary control, the current voltage control, to the power management, the power balancing and others, and also like into like energy management. This is why we want to see the data center in this way. And also talk about the grid side. There's a lot to talk. From the regulation of large-scale AI to AI load prediction using machine learning to predict, and just to talk about like a renewable integration and some new distribution grid planning, the demand side management, the grid scale energy storage, because the grid need to prepare for the energy, the power transients, so energy storage should be there. And also fast frequency control. This is related to like the power transient probably will introduce the frequency derivation. So then the fast frequency control need to be there. And also AI is very fast and can be programmed into as a supporting load. So probably people can leverage AI to stabilize a grid even. And also like customer adoption and education. Here concludes the whole presentation. Yeah. Dr. Chen, like either do you want to do this or I can do this?
Oh, please go ahead. I think there are already several questions, so you may want to relatively
answer them. Okay. So I will just quickly go through the summary. We already know that AI, we see AI as a unique power load to the grid. We see the different distinct phases demonstrate distinct power consumption behavior, right? So it has a low, ultra low inertia. It has a subsequent peak idle fluctuation. It has some unpredictable interruptions. It can also involve user behavior. So the challenge is big, and also we feel like there's a urgent need to do more research on this topic. I already cover a lot of the different topics, so welcome to ask any questions. I will try my best. We will try our best to answer those questions.
All right, thank you, Dr. Li, and also thank you, Professor Chen. So as we can see that there are several questions in the chat room. So I don't know if you can see it, Dr. Li. First question is, you can see the chat section. The first question from Hao Chi. He had 3 questions.
Yes.
So first one is if the dynamic load variability really interrupts the power grid in seconds level, could this problem be resolved by data center side cheap short-term storage like supercapacitor?
Right.
Yeah,
so
yeah, please go ahead.
Oh, sorry. Yeah, how about this? So I think we're a little bit over time. So maybe let's because I saw Hao Chi was leaving, so maybe we start from Anoop's questions on the variability of the data center load, and then go back to Hao Chi's question later after the audience asks the questions, right? So yeah, I guess I can try to respond to Professor Anoop Srivasta's questions first. So the question is like this, right? So does variability of data center power consumption is similar to the one in the slide, or the aggregate picture can be more smoother? So yeah, actually this is a good question. So I think this is also one limitation of our current research. We only did that for the MIT data center load. The other is our own small language model. So I would say the answer depends. So if we are talking about the ramping behavior or this kind of transient behavior, it totally depends on 2 factors. So one, how many users are submitting their query or submitting their prompts at the same time, right? The second is, do we reach the limitation of the so-called power throttling for a GPU, right? So if we always reach the GPU limits, then we would say the power curve is actually quite flat, right? But if the users just submit their prompts at a different time, right? So we can essentially model that as a distribution or try to get some real data, say quite similar to Google search query, say after some special event, say after election or after sports event, right? Then the analysis will be more realistic. And also want to mention one thing. We actually read into the Meta Facebook their report on training Llama 3.1, So they actually mentioned they were dealing with a lot of issue with utility companies about the power fluctuations. Yeah, actually the utility companies have complained to them, okay, the power is really fluctuating. So yeah, we do think the issue exists and it can become much more intense in the future.
All right. Thank you, Professor Chen. So, yeah, I also have a question from the audience. In page number 69.
69. Okay.
Hopefully, can you please go ahead there?
Yes. Yes. Give me a second.
Yeah, how do you calculate the W coefficients?
Oh, that's a challenging one. Actually, currently there's no like a very specific way to calculate this term from what we learn and what we observe. The easiest part probably is the training part because we can control the peak power and the checkpoint timing. So this one can be kind of like a well controlled. For the fine tuning part, it really depends on the data that you want to like somehow relearn or learn better. For the inference, it's really close to, really related to the user behavior. So we consider that part is quite stochastic behavior. Talk about the training part, even if we go to detail about training, if we remember the case, talk about the Meta, right? Even during the training, there's a lot unplanned stop, unplanned interruptions. So those interruptions means the power consumption will drop immediately, probably to the idle. So this introduce the power transient eventually. So this term, like the term, really will be quite complicated. So this is why like we want to analyze different models, different architecture, and even different hardwares, right? So this will all contribute to the calculation of the model. If we go deeper, like just pick one model, one hardware, and really like calculate each step of the training, like what we showed before, like those steps that consider all the data transfer and the calculation in each step, we can have this gigahertz or megahertz level equation really accurate, and probably we can scale up into like a seconds. So this is probably the future, one of the future direction of this. So yeah, thanks for the question.
Mm-hmm. Sounds great. The next question, are there any weekly or monthly behaviors of the AI load? What types of resources can be coupled with LLM training consumption power?
Yeah. For the weekly or hourly, for the training part, actually, I think it's more algorithm determined. So it can observe a certain behavior, like the one that we show here, like this one is very typical. So if you can imagine this model like a 100 larger and probably not only 100, maybe millions larger, and then the time can be weeks and months, then this behavior will be quite similar to that one. Instead of showing several checkpoints like the power dip, in that scenario, the power dip will be many. I've been heard like Meta or like some big company, they do this 5 minutes checkpoints. This means like the power transient will happen each 5 times, each 5 minutes. This will make sure like their training won't lose too many progress, right? But without careful planning and algorithm design, this will definitely cause a large transient. This means the whole during the checkpoint, the training stop, the power consumption will go to very low, like only because checkpoint is doing the saving side, so it's only deal with the data transfer energy power consumption. It's be really low. Yeah, so in general picture, training is algorithm determined. And if we talk about like inference, this will be user behavior. We'll probably see really clear, like the workday peak, like the daytime peak, similar to EV actually. Yeah.
I see.
But just
And any
yeah.
resources can be coupled with this kind of behavior, like renewables. Do you think?
You mean to make sure the renewable and the AI be complementary with each other?
Yeah, I'm
Yeah.
thinking about that.
Yeah, for sure. Like if we can predict PV or wind really accurately, then we can plan the training like align with the power generation of renewables. This is a really interesting topic, but we should notice like those big companies try to do something like on the opposite direction. They want to build a nuclear power plant. They want to make sure that the power, we do not predict the power, instead the power be extremely stable, and then at the same time maybe really low emissions. So what they do is really challenging the renewable adoption trend. Yeah.
Okay, thank you. So Professor Chen, do you have anything to add?
Oh, so yeah, I think about the this kind of timely or weekly behavior. I just want to add one quick thing. Yeah, it's also related to weather. So for instance, during summer, the data center PUE most of the time lower due to you need to put on more air conditioning, right? So yeah, basically you have seasonal behavior. During summer, the load can be usually higher. Especially those data center load is the same, but during summer the PUE is lower. Yeah, and daily, yeah, you have also a pattern, especially during hot weather. Normally your PUE or the total power consumption is higher during the middle of the day.
I see. Yeah. So yeah, so Professor Wang, on your side, do you have did you have you collected any questions, or do you have any comments?
Right. I think this is a wonderful presentation, and we can see, I mean, the audience are coming from different domains. For me, number one, I feel when we have a data center, for example, I'm engaging with some data center, this individual experiments down here will aggregate, and the total consumption will not fluctuate so much. Therefore, I wonder how does the big picture look like when we compare maybe data center consumption at the substation level at, I don't know, distribution grid. And second, I do want to know, for example, on page 77, maybe this page, 77, yes. So here, I mean, there's a training performance like 1 kilowatt. And so are these numbers coming from your computer? So those are my two questions.
Yeah, I can try to understand the second really quick. So yeah, the number is from our hardware setting. So we do set this power supply unit maximum support, maximum power consumption will be this, but in either condition it will be below. Like the picture showing later, like this one, we show this peak is around 450. It's very typical.
Right.
Yeah.
Okay. That's good to know.
So for the first one, I can try to answer, but also like Dr. Chen, if you want to add more, you can just jump in anytime. So yeah, I do agree. When aggregate everything, the curve will be smoothed out somehow. But we do notice something happening here. Even though people talk about like the training in distributed way or training maybe in a asynchronous way, but the training model actually will be quite synchronized. People talk about like using high bandwidth network to link with each other. They do not talk about millisecond. They talk about like even higher. So the model will behave like quite similar to one GPU behavior. So we still face this like a sub-second transient, somehow unplanned behavior of the whole data center. So maybe from the utility side, they more worry about big companies, big data center. If they train the AI model, how the AI model will impact the local grid. For the inference side, there's a huge chances and like the huge opportunities to do more, like smartly do this, smooth out the power consumption. We can encourage users to use a different time domain, even limit the user response account, or like increase the latency somehow into a certain degree. Then we can just smooth out the whole curve. For the fine tuning side, is a bit about this mix. I can imagine, even though big company will do the fine tuning, but a lot of medium-sized company or institute, like a research institute, they will do the fine tuning, because we probably don't have access to large-scale GPU data center, right? So we probably use several GPU cluster to train a domain-specific model, and for that we should pay much attention to like how the UPS responds to that, how the research institute data center behave. Still, this is somehow a thing we want to highlight. Also, like as Dr. Chen mentioned in the previous slides, nowadays the data, not the data, I mean the server stack already very high power consumption. Here, I may want to show this picture. So look at each server stack. The rack means like a unit of that. So it already reached 200 kilowatt. This is large somehow. And currently you probably need to over-design your system, add enough like supercapacitors and batteries inside the system. But later, then I can feel like the market will saturate somehow, and then people will care about like a more efficient way to do this. If AI keep going and keep like penetrating everywhere, then people will just need to know better about this whole thing. Yeah.
Right. How did you get the picture on page 77?
Yeah, I can go to 77. So the 77. Oh, sorry. So the 77, this one is from the online document. The people who designed the algorithm. This is the detailed information about the model. Unfortunately, Llama 2.3 is really like recently released. I don't get this the detail in like the layers, the hidden size, and attention health. I don't get that, but hopefully. Really soon, I think within next few weeks, the people will just tear the model apart, and everyone will know that. Yeah.
Right. And how about 78? So you show a large scale maybe deployment. So did you get this many GPU? I'm sorry, maybe next page. There's a page you show you actually use 200 GPUs.
Oh yeah, the one that the data from MIT data set. Okay, yeah, this one is unique actually, but this is the only good resource we found online. MIT willing to share the data set about their data center. I think this is more research focused data center, so we can see the peak power consumption is not so high. I think they limit the user access for the GPUs, so I don't observe like all the 200 GPU nodes working together, but we do notice like 100 GPU working together too. So the power consumption reached that peak level. Yeah.
Right. For our BDA community, so data sets are very important. So did you get this data set privately with MIT, or this is already public? So
this is public. Yeah, this is public one. Yeah.
So they can search MIT SuperCloud.
Yes, okay. Definitely, yeah, and their data set is 2 terabyte, and it needs some data cleaning and the data type transformation. This causes a lot troubles when preparing this slides, because the large data set sometimes is difficult to process. Yeah. we try our best to present a clean version of this. Yeah.
That's very nice. Thank you. Just those are all my questions.
Okay, thank you, Professor Wang. So, maybe it's time for the answers to how to choose 3 questions.
Sure.
So-
Yeah, I think
Yeah.
I personally know how to. I also can contact him after the.
Oh, that's why. I see.
Yeah, so yeah, but I would say yeah, both 3 are good questions. So I think we should also partly address the first question about using supercapacitor or some chip storage. Yeah. So I think the major point we want to make is yeah, it is possible. Yeah, but before making it possible, it's very important to firstly understand the data center load or the transient behavior about the AI load, right? So that's an interesting thing, right? And the second thing, yeah, like the BERT model, yeah, the fidelity, I think they do train the BERT model. So basically, I think yeah, this is like the training load under the settings on this slide 72. Right. And for the third point about the right, so the potential bias of using the local small GPT task to capture large LLM training. Yeah, so that's essentially our ongoing work. And yeah, thanks everyone for the comments. We actually try to scale up the simulation. Yeah, try to get a more comprehensive picture using larger GPUs and larger cluster of data centers.
So there's another following question in the conversation. I can quickly answer that. So for the data center side, this is not locally run, and the record is based on the MIT data center. And for other small scale model training, we do measure the power consumption locally in the GPU. So all the curve you see here, it's a GPU power consumption we captured in the local machine. Yeah.
It's like the PCC of the GPU.
Can I ask the question directly?
Sure.
Yeah,
Professor.
because if you measure it as a building level, then that load could include the air conditioning load. So I think that up and downs probably would be that, right?
Oh, for that, I need to clarify. So we specifically extract the GPU consumption in the MIT dataset. So this curve is only the GPU power consumption. They also record other power consumptions that we didn't include here. But yeah, if that's also like can contribute to our understanding, we can just do this later as a future work. Yeah. But I do notice they don't record the air conditioning side. They record the CPU side power consumption. So yeah.
So for the GPU side, are you? I think this measurement is important because if you measure that, are they measuring that from a panel or it is including some auxiliary ones because there are fans there inside? So I'm just wondering for the ups and downs, they could have been the GPU consuming that, but it could have been inside the device the fan is running, right? So that would be totally different.
Yeah, exactly. So they measure this based on using the NVIDIA SMI, the command, like abstract the information from the motherboard of the GPU. So this means like it is NVIDIA defined GPU power consumption. We do try to use like other third-party software to capture, like for example, the AMD power consumption. So like if you look at the later, those GPU power consumption is based on third-party GPU power consumption. I mean, we capture this based on not NVIDIA defined power consumption, but third-party defined power consumption. So the following work, like we're trying to like go deeper, is to directly capture the power consumption on the board, like trying to use other high resolution like stuff, like the scope, to capture like even higher resolution, because now this software somehow like we can consider this is software side. They can only allow us to go millisecond. But talk about like the training and the inference, we do feel like sub millisecond is also very important. So we want to go further deeper. Yeah.
Okay, thank you.
Thank you.